Our atmosphere, of course, presents an obstacle when we do the observations from the ground. Of course, atmosphere is of great benefit to us. It provides us with oxygen, which we need for life, and it also protects us from different types of radiation coming from outer space, but it does obscure the view. And in particular, there is an effect that is called atmospheric blurring, or twinkling of the star. Right? If you sort of watch the night sky, and then often it appears as if some stars kind of twinkle. Their brightness fluctuates, is reduced and then increased. And it's not intrinsic property of the star. What is happening is that basically if you are viewing the night sky from the ground, and here is a star that you are viewing, often in atmosphere a pocket of moist air comes along, and it effectively acts like a prism. The starlight will actually be bent by the medium provided by this cloud. So what happens to the starlight, it actually is bent and it's missing you. So there is a less intensity of the starlight that comes into your eye. And of course, as the pocket moves on, then the starlight can come directly into your eye. So what has happened is that for a while, the intensity of the starlight fluctuated, because when this pocket of denser air came between your eye and the star, it deflected, it refracted, I should say, the rays of light away from your eye, and the intensity of the light that reaches you drops, and hence you perceive this fluctuating intensity. Okay, so that is the problem with telescopes that are based on the ground, and to minimize the effect, astronomers typically put the telescopes high up where the air is thin and dry. So hence, often they are mounted in the Andes in Chile or on Hawaii. You usually try to locate a telescope where you minimize these effects. And I've shown one such telescope, Gemini North, in Mauna Kea in Hawaii. And of course, you can achieve much better quality of viewing if you do the observation above the atmosphere. So you place your telescope on a satellite, and that has been done and extremely successful. The Hubble Space Telescope operated since late 70s up until recently. I think officially it's out of commission, but we have learned through its operation so much about the universe, not just nearby, but at great distances from us, that it really profoundly changed our understanding of the universe. Also, if you want, say, to look at the X-ray radiation from outer space, and that's important when one wants to study the black holes. It turns out that black holes are also, and I'll discuss that in second half of this course in 1PO2, when we will describe the end stages of stars. Very massive ones, when they run out of fuel, they leave behind either a neutron star or a black hole. And it turns out that although it's black hole, and it's called black hole because nothing, including light, can escape from it, it turns out that they often suck the atmosphere of a nearby star with which they are gravitationally bound. And as that material accelerates towards the black hole, it emits X-rays. And we detect that there is something because we can see by this normal star shaking that it has an invisible massive companion, which is also the source of X-rays. And that's how we detect black holes. Of course, I mentioned in the previous set of lectures when we talked about the atmospheric windows that the top parts of our atmosphere block the X-rays and gamma rays, right? So if one is to do X-ray astronomy, you have to place your X-ray detectors in a satellite above the atmosphere.